You know, it just occurs to me I didn't say bye after the last video. So in that case, I'm going to say hi to start this one. Topic 7.07 Molecular Formulas. So last time you took a look at how you make an empirical formula, the simplest whole number ratio. But not all substances have an empirical formula. Some substances are molecules and therefore have a molecular formula. Now, you might remember when we did gram formula mass that the empirical formula is just simply a simplified molecular formula. So for the formula H2O2, you would simply divide by 2 to get an empirical formula of H2O. So let me show you how we arrive at these molecular formulas. To do the quantitative analysis necessary, what we have to do first is decompose the compound, as we mentioned, analyze the spectral data to identify what elements are in it, determine the percent by mass of each element, and then find the empirical formula. So this is what you've done the last few days. But what we need to do is take it one more step. To find the molecular formula, what we're going to do is to find the molecular formula given the empirical formula and the molecular mass. What the heck is molecular? How do you find the molecular mass? Well, I'm so glad you asked. The molecular mass is determined by using a very specialized gadget called a mass spectrometer. What the mass spectrometer does is take a sample of the element, heat it up until it loses an electron, and then shoots it through a curved magnet. Now, ions being electrically charged are affected by magnetic fields. The lighter a molecule or ion is, the more sharply it can be pulled around the turn by the magnet. The heavier the ion is, the wider it's going to take this turn. And so you calculate for each mass for your ion detectors what mass they're detecting. So for example, in this example here, any ion that takes this sharp a turn has a mass of 44. Any ion that takes this sharp a turn has a mass of 45. And likewise, any mass of 46 is heavier, so it takes the turn wider and has a mass of 46. Now, you can also use this to determine isotopic concentrations. So you take a sample of an element, you heat it, you ionize it, and then its isotopes are passed through the ion beam and separated out so you can find their relative abundance. But we can also use this for molecules. So here's how we find the molecular formula. It's actually really simple. The molecular formula is a whole number multiple of the empirical formula. So all you have to do is find the ratio of the molecular mass to the empirical mass to get that multiplier. And the first clue is the molecular mass. The molecular mass is 42.0. We have an empirical formula of CH2. That's all we need to figure this out. So first, let's find the mass of that empirical formula. We have CH2. Each carbon is 12.0. Each of the two hydrogens is 1.0. So our empirical formula has a mass of 14.0 grams per mole. Now, 42 is going to be a whole number multiple of 14. How do we find out what whole number multiple? Well, how many times does 14 go into 42? So you take the molecular mass, the bigger mass, and divide by the empirical mass, the smaller mass. And that will give you a whole number ratio. And what this tells us is that the molecular formula is 3 times bigger than the empirical formula. And since the empirical formula is CH2, multiplying out, we'll get C3H6 as our molecular formula. It doesn't matter what numbers they give you, it's always solved exactly the same way. Easy peasy. Take the molecular mass that's given, divide it by the formula mass of the given empirical formula. This will give you a whole number. Multiply that by the empirical formula, and that will give you the molecular formula. And that's all there is to it. Even if I gave you another example, it would be identical to this one. And therefore, I shan't give you another example. And so that I don't cheat you guys this time, as usual, I will end this recording by saying bye.